everyone. Welcome back to the Internet Report, where we uncover what's working and what's breaking on the internet, and why. This week, we're taking a break from our usual programming for a special conversation with Kamal Shankar, Principal Internet Analyst at Cisco Thousand Eyes. A seasoned network engineer, Kamal focuses on research and large-scale outage analysis. Kamal is joining us to discuss research that the Thousand Eyes Internet Research Team conducted on the effects of packet loss, revealing the surprising impacts that even 1% of packet loss can have. I'm Barry Collins, and I'll be hosting today with the amazing Mike Hicks, Principal Solutions Analyst at Cisco Thousand Eyes. As always, we've included chapters in the episode description below, so you can skip ahead to the sections that are most interesting to you. And if you haven't already, we'd love you to take a moment to give us a follow over at Spotify, Apple Podcasts, or wherever you like to listen. Kamal, the impacts of packet loss have been extensively researched, yet they remain often misunderstood. Tell us about the research you've undertaken.
Yeah, packet loss in general is an ability of packets traveling across the network to reach their destination due to different reasons such as congestion, signal degradation, hardware or software issues. It can be related to routing, buffer overflows, or security-related issues. In general, network community at large understand that packet loss is bad, but it's actually not really well understood on how bad it is, right? So as part of this research, what we wanted to do is to double-click into exactly that problem, as part of which we wanted to quantify these negative effects of packet loss. So we actually established a topology where we were able to test in controlled environment what are the negative effects of packet loss.
And to sort of extend on that, really, if you actually think about it from a real world scenario, the network operators focus on these big lumps, these big sustained spikes in packet loss. And it's very easy to see, I've got 100% packet loss, I've got 20% packet loss, and you can actually see what's happening. That is stands out. This is where we want to go. But what they often ignore is these small increases. And remember, we're talking about a complex interaction of multiple dependencies that come across there. And the way that loss is impacting at any one time can have this negative effect. And because they're looking at such small numbers in some cases, sort of like 1-2% packet loss, they tend to ignore what they are or overlook them to say this isn't a potential cause of a problem. So what we really wanted to do was to understand what are these low levels, what's the impact can have, and how much of a degradation it can actually cause.
Can you break down how the testing was done to explore what happens at those lower levels of packet loss?
In general, what we did is we daisy-chained 5 different hosts, and we tested in symmetric and asymmetric topologies, as part of which we configured routing. And it was a simple setup, in fact, if you think about it. Due to the fact that we utilized hosts with single gigabit Ethernet card, we utilized concept of VLANs to configure the routing. And then we just utilized static routing end-to-end to enable connectivity. And in general, we had a client on one side, a server on the other side, and we utilized a popular open source tool called iPerf to measure the throughput between those hosts. We did this in 2 topologies, as I mentioned before. The first topology that we did this in was a symmetric topology, where effectively the forwarding path is exactly the same as the reverse path. And then in the second topology, we did this asymmetrically, where the forwarding path is different than reverse path. We wanted to simulate 2 common scenarios. The first one with symmetric path was the typical enterprise network that would have everything configured symmetrically due to the fact that it's much easier for troubleshooting purposes. So effectively, if you narrow down where the loss or spike in latency or whatever the network condition might be, network operators would be able to easier detect and then focus on the problem itself. While asymmetric one is closely reassembling what we commonly see on the internet today. So effectively, majority of the paths on the open internet are asymmetric in that nature. So which means that forwarding path is going to be completely different in reverse path. As I mentioned, we utilized iPerf tool to measure the throughput between the hosts in both of these topologies. And then we, in controlled environments, started to introduce packet loss using popular open source or Linux utility called TC, which stands for traffic control. So we started introducing small level of packet loss and then measured what we were seeing. But before we actually started introducing any loss, in both of these topologies, we established the baselines. So those were the numbers that we used to work with initially. And then later on, we started, measuring 1, 2, up to 10% to see what were the negative effects. So that's pretty much what was the topology and how did we approach this problem.
So going back over that methodology then, something I want to point out is the whole point of keeping it sort of very simple. And as you said, wanted to simulate real world scenarios, but we wanted to remove the potential for something else to be impacting. So we really just wanted to look at the loss rate and the impact of that. So we had this very simple one around there. So you said just the straight symmetrical path and then the asymmetrical path where we're coming back down a different path to do that. Then also we use iPerf, or can you explain why we use iPerf rather than sort of using a synthetic? Is because we actually wanted to control the payload and the packet so we could actually really have a controlled environment.
Yeah, exactly. It gives you the options. There were no other flows at the moment when we were actually testing this out, right? So we kind of remove all of different factors that could contribute to other problems, such as interface overutilizations, traffic being dropped from different reasons. We even removed complexities that arise from the routing protocol configurations and stuff like that. So we stick to really basic static routing end-to-end, a really simplified environment, and end-to-end controlled environment. And, looking at the topology, especially for the symmetric topology that we used here, it closely reassembles what you would see in enterprise data centers. Like it's really, really close to that. We control the latency, we control the environment end to end. So that's quite close to that. When it comes to iPerf, iPerf is going to try to establish the connection between the client and the server. And one of the things that it's going to always try to achieve is to send traffic at the maximum rate between source and destination. In this particular case, we stick to TCP as a control protocol here. And that's the protocol we actually made significant changes to when it comes to all of this. Now, when it comes to TCP uses several methods to manage packet loss events and recover from them, including duplicate acknowledgements, timeouts, explicit congestion notifications or ECN, selective acknowledgements or SACs, and congestion avoidance algorithms. But ultimately, we kind of ignored all of these different methods for the purposes of this one and focused on different congestion algorithms to see what they are going to give us when it comes to this. Now, historically, organizations tend to use congestion avoidance algorithms such as Renault and Tahoe, but they were slow at utilizing all the available bandwidth. So something needed to be done. So researchers created Cubic, which is default congestion avoidance algorithm that's present on pretty much every single major operating system today. Whether you are speaking about Windows that you are using for your daily purposes or Mac OS, or on the server side, most of the companies and people are using Linux. They're all by default using Cubic. And we measured everything by default initially using Cubic. But later on, we actually made a significant change in congestion avoidance algorithm, which we are going to touch base a little bit later on.
What were the main findings? How significant can the effects of packet loss be, even at lower levels of loss?
So in general, we were getting quite good values on the baseline for both symmetric and asymmetric topologies. So, this is testing within the topology where no packet loss has been introduced. So we were getting approximately close values for symmetric topology. For example, we got 804.67 megabits per second. And in asymmetric topology, we got 864.13 megabits per second. So, even though asymmetric performed a little bit better, values are quite close. And then what we did is we introduced the packet loss, and we started introducing packet loss on 1%. And what we saw in symmetric topology is that we got 235.5 megabits per second. And in asymmetric topology, we got 222.49 megabits per second. Which means that on average, 1% of packet loss caused a 70+% decrease in throughput, which is amazing, right? Today, when you think about these values, like such as 1 or 2% packet loss, it's kind of easy to disregard them as it's just a small spike of loss. It's nothing big. It's not going to cause any problems. But in fact, once you put that into perspective, using the throughput, decrease in 70.7% can make a significant difference and does make a significant difference. Imagine your data center flows, imagine your AI workflows, imagine your large-scale traffic operations, all of a sudden being halted to 1/3 of the capacity. That's pretty significant, right? Once you cap it. And you cap it by just introducing 1% loss. And, the thing is, like, these things can happen in different environments from different reasons, right? As I said at the start of this conversation, it can happen, as a result of buffer overflows, signal degradation to the maybe dirty fiber and stuff like that. So it's not like that you control environment always just by configuration. Sometimes you need to get your hands dirty and stuff like that. But ultimately, it's hard to control. And, it's quite easy, to Mike's point, to disregard these small values as, not being important, while in fact, they are causing significant damage. Now, I'm pretty sure we're going to speak about the fact that TCP works really hard in the background to keep us not being aware of these things. The thing is, like, if you are at home and you are trying to watch YouTube video or watch your favorite Netflix show and stuff like that, it's quite likely that you are not going to see these small amounts of packet loss, just purely from the fact that TCP is using different mechanisms in the background, such as retransmits and stuff like that, for you not to notice the negative impacts of this. And it's going to largely depend on the application type itself that you are interacting with. But in general, in different environments, in enterprise environments, in large-scale environments where large amounts of traffic needs to be pushed really fast between source and target, 1% of packet loss can make and does make a significant difference.
And I think the point on that as well is that we are talking about TCP here. So we are, as you said, there's various mechanisms to recover, but a loss is a loss. Ultimately, that has to be retransmitted again. So if we're dropping throughput, then we've still got to go back and retransmit that packet or that frame again. Now, depending, as Kamal said, on what the application is, that's going to have a different impact sort of downstream.
Can you elaborate on that decrease in performance that users may encounter? How might this impact user experience with a specific service or application?
And so in general, like, what you're going to see are significant slowdowns. So for example, like, if you are watching a video or something like that, one of the things that you would typically see is buffering and similar problems in the streams. Depending on the voice-related applications, you would get choppy voice. You would not be able to hear the person clear, or they would not be able to hear you. But in general, it reflects in overall slowness. Now, as I said, TCP really works quite well when it comes to obfuscating these problems from you. They just hide it quite well. And, as an individual user, it's quite likely that you are not going to see that. However, in these environments where large amounts of traffic needs to get transferred really fast from source to target, it really does make significant difference. Then the other thing is different applications are going to react to packet loss differently. And one of the things that Mike and I, in the future, as part of the network intelligence and research team, are going to look into and double click into is effectively exactly that question, right? How does it pan out for different application types?
Yeah, and that's important because it's also when within an application. So if you're thinking about a connection or a handshake at the start, we could actually time out and you have to go through that whole process again. So it can actually, in some cases, prevent you logging on. If you're thinking about a real-time application, you can't retransmit it. You've lost that moment in time. So this is where you get the gaps or the choppy conversations. But again, if we're talking about an application that is really just doing some sort of transfer down, putting information, so going back in time, FTP or something like that, so like a file transfer, in theory, you're not going to notice. It just might take a little bit longer. So it's a combination of things. It's where does it occur within that workflow or that process flow? But also then, as Kamal said, what are the characteristics of the application? So therefore, then how's it going to manifest? And the impact could be greater depending on what those characteristics are.
Based on these findings, what recommendations do you have for NetOps teams?
Again, it's going to depend based on those characteristics of the application. The first thing we want to consider, obviously, is I need to be aware of it. One of the things Kamal mentioned when we set these tests up was establish that baseline, understanding what it is. That isn't necessarily then meaning what is good, is what is suitable for you. Because if you're looking at an environment where you've always had this low level of packet loss occurring, it just may be that that has actually been impairing the application itself. So you need to sort of, clear the wood so you can see the tree. So you get that point. You get down to understanding what is your base level and your understanding across the entire service delivery chain. So understanding the different dependencies and things like that, how it cooks in there. And then in conjunction with how the application interacts with that network. And then you understand then we're going to input this packet loss on top of that. If I start to see a degradation or a variation, if we're sort of talking about jitter, if you like, in that packet loss, it's then really understanding where there is in that service delivery chain, or what component, and therefore then I know what action I need to take to sort of move around it.
The bottom line here is that visibility is paramount. The things like if you don't have end-to-end monitoring that's going to alert you when these things happen, you are in a significant problem and you're not going to be able to react to these. So you're going to be dealing with the outcomes of slowdowns and stuff like that. So what's going to happen, and historically does happen, is that you are dealing with the consequences of stakeholders complaining that something is not working, while you would be able to actually, in the first place, by using end-to-end monitoring, be able to proactively get those things resolved before you get escalations from the stakeholders, which is really important paradigm shift. Historically, we were just all focused on troubleshooting of something that already has happened and affected different service owners within the organizations. Now we are in a position where we can actually focus on deep level networking problems and negative outcomes of issues before they reach out to us, which is really, really important.
And it's that combination of signals. We talk about nuances here. If I'm looking visually at something, I might, like I said, see a very little spike in percentage loss. But that might have a dramatic impact downstream to that particular application. So it's, again, always viewing everything in context. As Kamal said, that visibility is critical. If I understand how things are connected together, I understand how they react to these different situations, then these small increases, which I would have previously ignored, then become relevant. And I can actually say, all right, I know if I get that slight increase there, it starts to throw this application off. So now I'm not looking for 100% or big magnitude of there. I'm looking for these small variations, which otherwise would have been missed. I'm looking at it in isolation.
What are the next steps for this research? Are there any follow-up studies planned?
So we already actually did a follow-up study when it comes to all of this. In fact, as I mentioned, we played significantly with congestion avoidance algorithms in this research. And as part of that, we switched over to BBR. Now, BBR is bandwidth and bottleneck round trip time algorithm created by Google. And it's the algorithm that has been created by Google to, resolve some of the challenges that they saw with Cubic. Historically, all of the challenges with congestion avoidance algorithms came from the fact that they were slow at utilizing available bandwidth. If you look at the history, you had Tahoe and Renault, and they pretty aggressively reacted to packet loss events. They would cut transmission rates by 2/3. Then Cubic came along, and it was discovered that Cubic function really works well for this particular scenario, but it was quite aggressive as well when it comes to reaction to the packet loss events, as part of which it would cut transmission rates to almost a half or something like that. Fast forward to today, Google spent significant investment and did significant research in BBR, as part of which they kind of abandoned historical approach when it comes to dealing with packet loss, and they actually utilize latency as the indicator of buffers being filled out. Right. So what happens is that the algorithm is going to try to transmit as much as it can, and it's going to use the latency as the indicator that buffers are getting filled in. So think about it like this. You are sending a certain transmit rate, and if they observe that a latency is going up, they are going to slow down transmission. And later on, gradually, they are going to try to increase that transmission. And by doing that, you are going to find on the path between the source and destination, what is the host that has the minimum transmission capability based on the latency signal itself. So you are using latency as indicator that buffers are getting filled, which is a significant change in the way that these algorithms are working. But one of the things that happened as a result of this paradigm shift that they applied is the fact that they are squeezing out the bandwidth much more efficiently. Now, we utilized BBR for purposes of this research. It's quite simple change to apply on hosts. Effectively on Linux operating system, it's like two to three commands. It's supported on pretty much every major operating system as well. It's been part of the mainstream kernels for 5+ years. So we tested this in exactly the same topology. So we did not want to change topology. So we stick to same symmetric and asymmetric topology. And we first established the baseline. So in symmetric topology, we achieved similar value to what we achieved with the Cubic. And we got 868.50 megabits per second for symmetric topology again. And for the asymmetric topology, we got 827.20 megabits per second. So then we started similar to what we did in cubic testing. We started introducing packet loss. And once we introduced the 1%, we got 794.06 megabits per second for symmetric. And for asymmetric, we got 763.42. Throughput in the symmetric networking topology decreased by 8.57 compared to the baseline, while in asymmetric networking topology, the decrease was even smaller at 7.7%. Now compare that to what we achieved with cubic, where we saw on average 70+% decreases. Those are significant and pretty amazing throughput gains that we saw just by switching congestion avoidance algorithm. I think it's an interesting data point for organizations that are serving quite large amounts of traffic. And if you think about it, pretty much major companies are using. As I said, Google invented this protocol, so they are using it itself. But there are other large-scale companies that are also testing it. So you will have the names of like Dropbox, Spotify, and other companies publicly speaking about some of the benefits that they saw in their workloads.
So I think what we need to say first of all with this isn't necessarily sort of panacea. We come back to the applications characteristics that need to be applied to that, because it can introduce other things. And in defense of the other congestion algorithms, sort of TCP is a very old protocol. I think it's even older than me. And that had these mechanisms built in, and it was designed to run over a quite a lossy environment, which is why it had that aggression, why you then start to see these sort of slow starts and things like coming on there. Now, to a degree, that's disappeared, which has allowed them, as you said, from a BBR perspective, to start to consider working on a latency from that point of view. I come back again to these application characteristics, and this is the next part of research we're going to look to do, is what characteristics of the application match that environment. Because it may be in some cases where, it's a direct benefit, and we've been testing this, and as Kamal said, we're seeing some huge benefits, and it will definitely improve from some applications. But in some circumstances, effectively, you just kick a can down the road for different application characteristics, in which case we just move the bottleneck somewhere else. So you still have the same impact in terms of a degradation to performance. It's just that you've removed that one part. So you're sort of chasing that down the line there. So what we're going to do next is look at the applications and the characteristics of the applications, then how they manifest to this whole environment, including the congestion algorithms on top, and which suits better.
That's our show. Thanks again to Kamal for joining us. And if you want to explore the team's research findings further, check out the free blogs linked in the episode description. Please give us a follow and leave us a review on your favourite podcast platform. We really appreciate it. And not only does this ensure you're in the know when a new episode's published, it also helps us to shape the show for you. You can follow us on LinkedIn or X @thousandeyes, or send questions or feedback to internetreport@thousandeyes.com. Until next time, goodbye.